everyone. I'm Naoji Matsuhisa, Associate Professor at the Institute of Industrial Science in the University of Tokyo. I work to deeply thank Epoch Foundation for giving me a nice opportunity to give a webinar at Young Innovators to Better the World. So today, I work to talk about my recent research progress entitled Smart Skin-like Devices for Future Wearables. Yeah. So I'm tweeting my recent activities in Twitter. So if you are interested in my talk, please follow me. Yeah, you can hear my updates. So this is what I'm developing. Soft and deformable and stretchy materials which can conduct electrical signals. And the reason why we develop such material is to enable the future wearables. So currently, this a watch type device or ring type device became quite popular because it can enable long-term monitoring of the body activity or PPZ or electrocardiogram. And this kind of long-term monitoring of biological signal is quite useful for preventative medicine or remote medicine or rehabilitation or training for sports. But as an electrical engineer, we are developing future wearables. And there are mainly three limitations in the current wearables because of the small and rigid form factor, like a watch or a ring. And the first problem is that because of the shape, the location is quite limited. For example, we cannot measure the our body temperature precisely from our wrist part. We want to locate our sensors close to our core body. And if we want to measure our body motion, we want to place our sensors to the joint part. So the body area sensing is quite important. The next challenge is to enable the motion artifact-free sensing. This is what I like to say that once we wear the watch or some rigid type device, especially during the sports activities, these devices can easily move on the surface of our skin, so that this can we cannot record the biological signals stably. The other important challenge is the comfort of wear. Even a normal watch, not a few people, don't like to wear because, if, for example, when once we sweat, we feel itchy on our skin, or this kind of issue is especially important for babies or people with dementia. It's a little bit difficult to tell them the importance of the wearing. So it is very important to develop a body area and motion artifact-free sensors or wearable devices with comfort of wear. Then the stretchability or softness is the key to enable such future wearables. For example, in case of powders, because of the stretchability, it can conform to our body movement. We can attach on the arbitrary surfaces on our body, and this kind of stretchy textiles are quite useful. So even if our body shape are quite different, it can nicely fit to our body. For example, even if you drink too much, still it can fit to your body. So stretchability is a key enabler to realize future wearables. So when the Apple Watch was commercialized in 2014, this Time magazine made this kind of image, and they say the Apple Watch is just the start, and they describe this kind of highly skin conformable wearable devices, and this is exactly what we are trying to develop. So already, researchers have found the advantage of this of showing the of realizing softness in the electronic devices. So uh, in this work, researchers precisely systematically tuned the softness of the elastomer sheet. And then uh, once the well, yeah, they control the softness by changing the thickness of the elastomer sheet. And once when the material is not so soft, when the thickness is 500 micron, we can observe a lot of gap between the soft sensors and rough skin replica. But once we reduce into the 5 micron, which is the softest sample in this samples, then in this case, there is no gap between the software electronic devices and skin. So because of that, we can significantly improve the contact of the sensor to the device. So we can improve the contact of sensors to our skin. So we can improve the signal integrity obtained from the sensors and comfort of wear. And also because of the softness, it doesn't disturb our motion. And the other study shows that once we move our hand, at the location of this point, at least 30% of strain is existing. So if once the device has the stretchability larger than 30%, it can completely follow our motions. So, although current wearable devices are rigid and compact form factor, in future we may be able to realize a soft and stretchable electronic devices. And because of the softness, even if we make it in over a large area, we can still keep comfort of wear. So and because of the larger area of contact, we can put a lot of multimodality. For example, we can place a lot of biological sensors to detect your disease in very early stage, or we can have a very beautiful display. Then we don't have to carry smartphones and smartwatches anymore. So the softness or skin-like achieving skin-like softness is very important for realizing future wearables. And in order to realize such a thing, the major challenge is with electronic materials. So usually the conventional electronic material silicon is very fragile, and once you imagine the elastomer sheet, usually they are fairly conductive. So it is very important to develop stretchable but high performance electronic materials. And this is first material I developed since I started my research. So this little bit white part is the material I developed, and this material can exhibit a really high conductivity, or even under 400% or 500% strain. So that because of the high conductivity, connected LED can maintain a very bright light. And because this material is easy printable and cheap cost, so we can alter by printing over the cheap and stretchy textiles, we can easily make electronic textiles. So in this demonstration, we printed both stretchable conductors and pressure sensors on the fingertips, so that we can knows a very small pressure sense of pressure in the finger, and we can obtain such a signal through this stretchable conducting wires. Another example is stretchable lithium-ion batteries. So in this work, we developed various stretchable electronic conductors and materials for stretchable lithium-ion batteries, and this material can store energy, and we can obtain energy, so even under 70% strain. So this would be a very good energy storage for future wearables. The and the stretchable sensors are quite useful for long-term monitoring of our biological signal information. So in this work, we realized a highly sensitive stretchable strain sensor, and then this sensor can sensor even a 10 micron strain by the large enough resistance change. So we can put such a sensor on the tumor, then we can precisely monitor the size of tumor. So previously, doctors had to use a caliper to measure the size of tumor, but in this case, we can just laminate the skin conformable tumor skin conformable sensor which can monitor the tumor size, and then the doctors can immediately know the important information. And stretchable electronic materials can be transparent. So in this work, by developing a highly conductive and transparent stretchable conductors, we realize the stretchable and transparent touch sensors. And we can see that when once we touch with our finger, then the corresponding part shows a peak on this PC screen. And of course, this can sense a mouse touch. And this stretchable and soft touch sensors can be placed on arbitrary surface, including our hand or some robots. Or yeah, this can be really a second skin to interface with computers or robots. And the stretchable soft sensors can be operated wirelessly. So you can see in this work, there is a stretchable strain sensor, and we can operate using the flexible readout circuit. And because our sensor is highly sensitive. So uh, although that we are reading out wirelessly, we can stably read out the pulse wave signals which locates around this area of our wrist. And these wireless sensors can be located in any places on our body surfaces. So in this case, we put the sensors to many places on the body surfaces, and we can form a body area sensor network. And then, for example, during we sleep, we observe the decreasing of the pulse rate or breath rate, or during the exercise, the opposite situation happens. So pulse rate or breath rate increase, and simultaneously we can monitor our body movement. And beyond the stretchable conductors, recently high-performance stretchable semiconductors have been developed. For example, our smartphones or PCs are supported by the silicon, which has a modulus, which is a parameter to measure the rigidity or softness of the materials. And in case of silicon, the value is 160 gigapascal. And recently, the flexible display has been commercialized, especially in the advanced smartphones. And in their case, they use a flexible organic oxide semiconductors, and the rigidity or Young's modulus is like 10 gigapascal. But the recently developed stretchable polymer semiconductors, they have a modulus of like 1 to 10 megapascal, which is significantly lower than those of silicon. And even if we stretch over 100% or 200% strain, this can maintain a really high electronic property like flexible semiconductors. And by fully utilizing such a unique, stretchable, unique mechanical and electrical property of stretchable semiconductors, we recently developed a stretchable and high frequency diodes. The key feature is that this is the first device which can operate at 13.56 megahertz, which is a frequency we use in the RFID communication, which is we usually use in our transportation cars. And we integrated such as stretchable and high frequency diode with a liquid metal based stretchable antenna and stretchable display and stretchable sensors. And in this way, we can receive the power wirelessly using this antenna, and with diode we can operate this display and sensors. So in future wearables, we may laminate our device on our skin, and after some usage, we want to charge our device. But connecting cable onto your skin is kind of awkward, and it can strongly disturb our daily activities. But with this stretchable high frequency diodes, we can wirelessly power the device on skin, and we can stably operate the sensors or displays on the soft devices. And recently, we also enabled stretchable light emitting diodes. So you can see this device can operate very stably even under 100% strain. And then this kind of high deformability will enable the future skin on-skin displays. And once we can precisely monitor our signals by the soft and stretchable sensors, and such information can immediately displayed by this kind of stretchable LEDs. So this is end of my talk. So although the conventional electronic materials are kind of rigid, and which is far from our which is far from the mechanical property of our skin, but recently developed stretchable and soft electronic materials can enable the next generation soft electronic devices and soft electronic systems, and with that we can enable the novel applications. Yeah, so this is the end of my talk. I'd like to thank again the Epoch Foundation, and thank you very much for listening my talk.